Yes, my name is Lowell Lamb. I work in the core switch group at Broadcom. And today I'd like to share with you some news on a device that's just now coming into the market from Broadcom called the Trident 4C. All right, we have, of course, a safe harbor statement that concerns mainly forward-looking statements. So we ask anyone listening to this call to consider what is written here carefully. All right, we've, I think, in previous discussions, described how Broadcom's switching portfolio, our switch ASIC portfolio, we have three independent architectures that have been optimized for the three major market segments, the enterprise market segment, the service provider market segment, and the hyperscale data center segment. So, of course, these have different since they have different jobs, they have different feature sets. But one of the things that we've seen all across the entire market is that there's rapidly growing interest in visibility and security. So that's what I'd like to talk about today. This device, which is our, get rid of this, the Trident 4C. This is the industry's fastest security-enabled switch ASIC. And by that we mean this device, which has, it's a 12.8 terabit switch. It has 256 50 gig SerDes, and it supports data rates from 10 gig to 400 gig. It can perform fine-grained security analytics on the entire traffic load. And this is all performed in hardware. And so you can see some of the numbers here. We'll dig into how we got to the scale of performance. But it is meant to really move the needle on what can be done in providing visibility to the entire traffic load. And it is also designed with the with working copacetically with AI ML-based threat detection, and it's also suitable for many configurations, either fixed configuration devices or chassis-based devices. All right, so I don't think I have to tell this audience that security is important. I looked over the resumes of the panelists, and I see a lot of network security experts. So I do hope that you join in, you chime in, you help flesh out the story, or at least give us an amen on the important points. All right, so the first thing I'd like to talk about is just to give a broad brush discussion of what kinds of attacks. When we say a network attack, a security attack, just fill that in a little bit. There may be folks who are listening in who really haven't looked hard into its network security. So you'll hear on the left, there are many, many kinds of attacks: port scans, DDoS attacks, teardrop attacks, and so on. This is a long, long list. And in fact, that's the message. There are many, many kinds of attacks. The reasons for doing this are actually quite concerning. Sometimes the attacker is basically checking every door and window to see if there's an open door into your network. So reconnaissance, this would be a port scan. Theft of digital assets. Basically, I want to hack your network and steal credit card numbers, social security numbers, or very sensitive IP. And then for many reasons, there are many nefarious reasons, there are denial of service attacks. Basically, someone just doesn't like you and wants to take your network down. And there are lots of, you'll hear lots of names for these various attacks. These attack vectors are just a few of the common examples. There are many, many other attack vectors. Now, because all of us, from the largest corporations and governments down to individuals, we're moving more and more of our digital assets into the cloud. That means there are more things worth stealing or disrupting. So in several dimensions, network attacks are growing steadily. They're growing in terms of volume and sophistication. And so what that means for Broadcom is that as we help build defenses against these attacks, they have to scale with switch bandwidth, and they have to be agile and adaptable, because the attacks of today will not necessarily be the attacks of tomorrow. So we have to be able to meet challenges as they appear. So I can't cover everything in one 30-minute discussion. What we'll focus on as an example today is what do you do about DDoS attacks? Okay, these are growing rapidly in popularity, in nefarious popularity. And so I think that talking about this will illustrate the kinds of tools you need, which also will apply to the other classes of network attacks. So what is a DDoS attack? Well, DDoS stands, of course, for distributed denial of service. All right, so a denial of service attack is any sort of malicious attempt to disable or occupy network resources. All right, the second piece of this is the distributed part. And the way the pros talk about this is they talk about an attack with a large attack surface. What that means is you're not going after one point, one port on a network, or one resource. You're targeting many, many parts of the network at once. And if you think about it, a network has lots of critical pieces, many layers, their hardware layers, their system layers, software layers. All of them are critical, and they're all tightly coupled. So the term DDoS is very broad. DDoS, it's a big bucket with lots of different things in it. Basically, anything I can do to gum up your network, whether it's occupying all the bandwidth on the access ports, or if it's occupying all of the sessions in a session table somewhere, or if it's occupying all the computer memory, anything that gums up the plumbing is a successful attack. And so just, instead of saying it can be anything, let's use as the example today, just imagine an attacker who's just flooding the target network with a high volume of junk traffic. Okay, so this is very common. This is a very common category of DDoS attack. I'm just going to flood your network with junk traffic, and the junk traffic, because it's distributed, is originating from multiple sources. Now, I am not a master of this. I am a student. The more I learn about this, the less I know. If you want to really dig in, there's a modern book that's quite good, Osilic and Brooks. This is strongly recommended if you want to learn about DDoS attacks. Okay, so using a diagram, here's our DDoS attack. You have some malicious actor. Here's your attacker, and he wants to disable this target application. He basically wants to gum this up somehow. It's some critical application running on some server somewhere. So this attacker has access to a small network of command servers and a large network of bots, as they're commonly called. And these bots are the devices that actually generate the junk traffic and flood the network. And they come in across this broad, they don't come in on a single port, they come in on many ports in this example. So distributed, again, it means it's coming from everywhere, or from many sources. Attack volumes can be pretty big. I mean, there are examples quoted, or at least publicly acknowledged, where attack volumes have peaked in excess of a terabit per second. And typically, the source addresses are spoofed. So you're sitting here, you're watching all this junk come in. It's really pointless trying to figure out where it's coming from by reading the source address, because those are all spoofed source addresses. So this is our simple example. Now, if you don't want to do this, if it's too much trouble or there's too much risk in building such a network, you don't want to get discovered, you can hire someone to do it for you. And I find this, in fact, deeply disturbing, that this is now a business. And so this guy, the yellow bot herder, he is working all day, every day to make this work better. The prices are low. You can start, I've read, for as low as $2 an hour. You payable in cryptocurrency. And I guess you get one. I don't know what you get for $2. The more you pay, the more you get. So many other architectures are possible. Now, the most common method for defending against DDoS attacks is something called anomaly detection. What is anomaly detection? Essentially, you create a time series of network traffic, and this time series, and then you look for DDoS attacks. Okay, you can look at the whole traffic load, or you can look at some sample subset. And then you do fine-grained, take fine-grained time slices, 100 milliseconds is common, and you plot it like this. The observed traffic parameter can be basically anything: bits per second, packets per second, session requests, or it can be derived values like the entropy of header fields. So there are many, many choices here. So you just build these time series, then you perform analysis. Now, the analysis can be either based on statistics or machine learning. Machine learning is quite popular. And what these threat intelligence engines do is they establish a baseline. So healthy traffic looks like this, and they establish thresholds. And now you need to do peak detection and event discrimination. So the questions become, can you pick out the DDoS attacks? And are you sure? Okay, that is not a facetious question.
Yep. False positives are always going to be your big, yeah.
Yep.
Yep. You got it. And so in this example, you get 2 good detections. Here, this is a DDoS attack. You get 1 failure and 2 false positives. And this is not academic. I mean, there's real money, for instance, on the table. For instance, let's suppose you pay tens of millions of dollars for a Super Bowl ad, and it's a good one, and people like it, and they want to go to your website and buy whatever you're selling. And so this is real traffic from real users. But if you interpret this as a DDoS attack and you shut these people down, that wasn't the intention. Similarly, over here, if you miss this one, you might think, oh, I'm getting a bunch of customers coming in. And if you're in a hosted service, that means that you're spinning up servers you don't need, and the meter's running, and you're paying money you didn't need to spend. So again, this is where the pros spend all day, every day, trying to do a better job of looking at these time series and interpreting them correctly. So,
and the other problem you have there is in the actual DDoS attack, you have to determine which of that traffic you still want to go through to your site,
exactly,
and which you want to drop.
Exactly.
Some of it's legit.
Now this is a really hard problem. The more I learn about this, the sicker it gets. This is hard. So anomaly detection schemes, they are not perfect, okay, as we just discussed, but they're not going anywhere. They provide the only protection we have against new threat vectors. That's a big point. That when new things come online, you're still going to get disturbances in these time series. So how do we improve performance? So broaden the attack surface area. This is what we're pursuing. Eliminate sampling. Improve the interaction with upstream systems, which are part of the story. And then also, because of the bandwidth involved, you have to automate the event fingerprint detection. All right, and there's a feedback loop we'll talk about. Okay, so in terms of expanding the attack surface area view, what they mean, and I've sort of blown up the earlier picture. Here are your attackers, and now inside the network you have edge boxes and a core switch or an aggregation switch. The edge boxes, since they only see a few of the exterior ports, they have a limited surface area view. The big box in the middle, this is the aggregation or the core. Since he sees many of these now by way of the edge boxes, he has a large surface area view. So this has to happen. You have to move your analytical capabilities into the aggregation and core to increase the surface area. Okay, everybody understands this. This is not a new idea. Okay, this helps you deal with the distributed part of DDoS. The challenge, of course, is that at core speeds, this is really hard. If you think about it, you have to crack open every packet that comes in. You have to pull out the data you're interested in. You may have to process it. It's just really hard. And bandwidth frequently exceeds 10 terabits per second. So a common cheat is, oh, well, we won't look at every packet. We'll sample. We'll pull out one packet in 1,000. We'll pull out one packet in 2,000 and create these time series and then perform the analysis. Let's hope that's good enough. I don't think it's a very hard sell. It's not good enough. Imagine going to the airport and you've got 1,000 passengers or packets, and you pull out one out of every 1,000 and send them through the security scanner. Okay, that's better than nothing. That does improve airport security, but it doesn't make the passengers comfortable. Okay, in fact, this is what you want. You want to scan every passenger or every packet. And once you do this, of course, you now can also use the fact that you have all of the data to start to build connection level patterns. In other words, if you get 10 suspicious people coming in and they're all headed for flight 1, 2, 3, that's worth knowing. And that's the sort of thing that's very hard to do with sampling. And this shouldn't be a surprise to anybody watching this. If you look at this time series, this is a classic signals to noise ratio problem. You're trying to dig really subtle signals out of a very noisy data set. You know, the figures of merit and statistics, things like signal to noise ratio, variance, and all this, typically scale with the square root of the number of samples. So square root of 1,000 is 33. I mean, you're going to get, you know, I think it's a very reasonable to expect you'll get at least an order of magnitude improvement by going to full scanning as opposed to sampling. So now let's talk a little bit about the device, and I hope this motivates why we've done what we've done. Okay, and I should say we're very proud of this. This is the 4th generation of this technology. We've been building this for low bandwidth edge boxes. This is the first time we've been able to bring it into a core device. So there are 3 big pieces. So again, here's our attacker. Here's our bot, and he's going after this target application. So we have there are 3 pieces to the engine. There's a flow table. There are what we call flow groups, and then there's this export engine. So the flow table, this is where we track the individual flows. And there are, we have over 500,000 entries, and for each of these entries, we have fine-grained meters where we track packet by packet what's going on with these flows. The flow groups, okay, this is where we can define, okay, we want to look at the entire traffic on the switch or some subset. This can be a port, a subnet. It can be all the traffic going to some particular application. It's extremely flexible how you pick out the subset of groups of flows that you're interested in. This is also where it has aggregate statistics. So this is where you roll up the statistics across all of the flows in the flow group. And this is also where you can download particular fingerprints and put thresholds on them so that if you cross the threshold, you generate an alarm. And we'll talk about this in just a second. These flow groups, this is not a static picture. These can be dynamically created and deleted as the threat environment changes. Then finally, there is this flow record export engine. And so this is what talks to the threat intelligence engines called formally collector analyzers, which are upstream. And this has, I should say, all of this is in hardware. There's not a pool of processors running software to make this work. All this is in hardware. You can automatically build packets and export them up to 8 different collector analyzers. So you could have one looking for port scans, one looking for HTTP protocol attacks, and so on. And so the way it works, and this is, we have 10 gigabits of bandwidth, so you have lots of capacity to talk to all of these engines. Okay, so the way it works just in this cartoon is basically this builds this part builds the time series, and this is the computationally, or you had to, this is computationally intensive process. Crack open 5.5 billion packets per second, pull out the fields, do whatever checking is necessary to find out which flow group it goes into, and basically build these time series. This is very, very intensive. So then we build the time series, forward them to the collector analyzers. Then the collector analyzers, the intelligence upstream, does the analysis and finds the attacks. And then based on this, can send back updates and reconfigure the engine and do it again. And so, for instance, if you, on this peak, you say, aha, I think we're under attack, this engine might say, okay, I want to fire up 50 new flow groups to check all the subnets to find out where this is coming from. And in this case, sort of, this is an example of iteratively drilling down. Now, I'm going to just pause for a second. If you think about it, we have broken the architecture along what we believe is a very natural boundary, that as the threats evolve, the intelligence will continuously evolve to track the threats, but you're always going to want these time series. And so this part of it is relatively stable. So we've broken the problem from the hard part, which we've moved into hardware, but is very stable. You'll always want these time series. And then this blue stuff, this analysis, is, relatively speaking, computationally light. This can continue to evolve with the threats, but we have in place the hardware engine to supply these time series. We can build, I should mention, theoretically, I think it's millions of time series can be supported simultaneously. The real message is you can generate for these analyzer engines as many as you want. There's no upper limit to how many of these can be generated simultaneously and sent upstream.
That's a good thing, because I was just thinking, I work in the educational environment, and
right.
What looks like a baseline one day of the week is going to be a completely different baseline.
You got it.
3 months away. So.
You got it. And also, our customers, they're providing this piece. And sometimes it's an equipment manufacturers, there are third-party outfits that just do security. And then sometimes the biggest customers, like the biggest cloud guys, they roll their own. And that it's proprietary. What's actually going on my network, we don't share that. And so what they want is they want us to give them this intermediate level of information. Just give us the time series. We'll figure out what's going on in our network. Okay, this is just, okay, you said it's big. Okay, we can do 5.4 billion packets per second. And the earlier if you're actually talking about full inspection, there is only edge boxes are available now. That's the basic idea. That this is the first device that's capable of working at this level of performance in the core. Same thing in terms of connections, that we can handle 500,000 connections. The only other things in the market are 100,000 or less, 100,000 or fewer. So that's basically it. And so now you can understand where these numbers come from. That we need 500,000 flows. We track that. This is how many packets you have to open up. You need almost 200 billion math operations or ALU operations to figure out, once you've broken open the packet, what happens to the various fields and how to update the counters and so on. Now, the final thing I would say is that this was not designed for appliances. This is not meant to be a specialty device. We fully expect that this is now it's rapidly becoming a mandatory capability in standard switches that will be used in many places in the network. And so we expect, and we have high hopes, that there will be wide-scale, high-volume adoption of this device for standard switching applications throughout the network.
Obviously, you mentioned earlier that a lot of this has to do with being able to detect exactly which packets drop and which to pass. There's a lot of specialty vendors out there, both in the DDoS space like Arbor and in the security space like Palo Alto, Juniper, Fortinet. Do you have a mechanism for these specialty vendors that really know good from bad to be able to feed back into
absolutely
to take care of this, and who's already signed on and working with this?
Oh, absolutely. What happens here, and here's the example. Okay, so you send up the time series. The threat intelligence engine says, you know what, we've got a problem, figures it out. And then sends down queries, I want more data, or it sends down, I want to fire up some new flow groups, whatever. It also can update the configuration of the switch. And so we mentioned at the very end that we have these ACLs. And so you can just put, okay, I found out who the bad guy is. I'm going to put ACLs in place and stop him, drop all of his traffic. That's exactly how you use it.
So do you have any of the major players in these spaces that are doing this now that have signed on to
we have
use their intelligence to your switches?
Yes, we have designs in flight with big companies whose names you've heard. Yes, and a lot of the reason being, and we were going quickly. We all have had, for the last 4 years, we've had this capability in these edge boxes, so below a terabit per second typically. And so there are already people out there who use this capability at a lower scale, and they put their brand on it. They don't tell you that it's us underneath, which is fine. And so they are already designing with this. So yes, it's already out there.